That's the second vessel we saw in our line out there. The internals on it are not too different. Fluid comes in here. If you'll look, it's got a diverter plate. Anywhere there's a fluid inlet, you'll see that diverter plate, just like was on the model in the lab. So what does the diverter plate do for us?
Diverts it.
Why? What's good about diverting?
A little extra separation.
Why?
Change of momentum.
Change of momentum, right? You're not answering any questions.
Yeah, I'm sorry.
No. Okay, change of momentum, right? So all this has a diverter plate on it. That's going to help the gas separate from the oil and water. You've got nearly this full area here to work with separating oil and water. It's got an internal baffle in it. Water dumps out here. This plate would be replaced with one that's got the ball in it. It's got sight glasses to adjust that level. This has got a bucket in it. You can see the bucket. It's a square container in there. It's got a quieting place where that float can work. And then it's got the dump for the oil. Okay? Okay, I've got a lease. We've got several wells coming in. I've already run the production through a separator, but I've still got oil and water. But haven't got near enough water to use this, so what we got to put my next vessel in after that. It's already been through a separator, but I still got to separate the oil and water. What's the next vessel you'd put? Anybody vote for heater treater? It sounds reasonable. Okay, let's go look at a heater treater. Okay, this one, a lot of it we need to see from the inside on some of these internals. Okay, you can see at the bottom how the fire tube's shaped. The fluid enters where? Where does the fluid come in? Up here? Huh? Come on, where's fluid going in a heater treater?
On the bottom where the heat is. No, it comes on the top.
That's not the top.
Where's it go?
It goes on the top. I'm not sure which one it goes around.
Well, how many choices you got? These are sight glasses. It's got an opening there. You've got a clean-out plate over here. So how about we enter right here?
That sounds good.
Okay? Fluid's going to come in through where that little plug is screwed in right there. Now, when it comes in, it's going to hit this plate. Remember we talked about a solid plate? Can you see? It hits this plate. That becomes a gas separator in this remaining area here. So the gas can go up and out. Our fluids are going to go down this pipe. Through here across this baffle will spread fluids across the diameter, but it goes all the way down, hits a diverter plate, and then floods past the fire tube. So our oil and water emulsion goes all the way down. We set our water level so that it's above the fire tube, and then as this continued emulsion comes through that water bath that's heated up, it'll float on up, and then we're ready to take our oil off. Where would we take the oil off? Where's the oil come out of a heater treater? Where, Miss Bessemer? Right there, yeah. Yeah, so now we got fluid coming in here. It's made the journey all the way down to the bottom. Oil and water have separated. Oil comes back here. Now we got to take the water out. Where is it? It's way down here, isn't it? And remember, it comes up through that. Some people, it's called a grasshopper, or the water boot, the water leg. Comes up here. Here's our device for telling it how high to go up or down. And then when we take the water off, we come out this opening right here and down to our dump valve. that water comes out, down, or water comes out, excuse me, here and down. Oil comes off the top and out. And then, yeah, gas is off the back pressure regulator. Okay? And that's a heater treater. Now there's a couple other tubes we didn't talk about. Up in the very top, remember this is sealed where the gas can't get down here? There's two tubes. One of the tubes extends up almost all the way to the top, but to make sure it's in the gas state, in the gas phase, and then it comes through the plate so that we get our gas pressure equally through the whole treater. So we've equalized the pressure across this plate with this tube. This tube comes down through the plate and enters the water leg so that it equalizes the pressure in it. So every part of the separator
Have the same pressure.
or every part of the treater and every part of the water leg are equalized with that gas pressure. So now all we're left with to open and close the valves is a hydrostatic head. Make sense? So we're selling oil now out of the heater treater. Let's look at a separator. We kind of skipped over it. I only had one well, makes a little bit of gas. We bring our fluid in to the side. Gas comes out the top. Remember we talked about mist extractors. Look in right there and you'll see the mist extractor in that separator. Now that's pretty small, but it's the actual same type of material that's used in a full-size mist extractor. So go ahead and have a look. So it just looks like you had a necklace and just threw it in the jewelry drawer, right? My wife makes jewelry. I'm very familiar with it. So look at all those tiny openings in that. That's all designed for coalescence. So as the wet gas stream passes through that, that gives it lots of surface area for those little droplets to condense and become bigger and bigger droplets. And as the droplets get bigger, they fall out. They'll fall down into the liquid space down here. So our mist extractor sits right here. Where would the safety relief valve go?
Right on top.
Right on top of the mist extractor?
No.
Where? Right there. It's got to be off to the side of it. So that's an opening that opens all the way down into the vessel. If we don't want to put a mist if whatever area our mist extractor covers, our safety relief valve has to be off to one side of it. The mist extractor generally does not cover the whole diameter of the vessel. If it did, we can even put the safety relief valve on the side. So safety relief valve, gas outlet. And then the only other thing about it is it's got a plate in here, so as this fluid comes in, it strikes that plate and it keeps it from hitting our ball float. Remember that lever arm that we had in there? We've got this ball floating on the other side. So to keep from jockeying that ball up and down, it's got a plate to kind of stop that movement. So when we put our ball float in here, and then our water outlet, or our fluid outlet down here. Okay, so there's only one other vessel we haven't looked at. And what's this? We haven't talked about it. When we go on the Oxy field trip in April, you will see a lot of these. These are called gun barrels. And Oxy as a company has decided they will not use heater treaters anymore to treat their oil. What they do is bring the fluid in to the top of this big tank through here, take it down to the bottom, and then on bottom is a spreader plate that spreads that fluid out so that the oil and water have a chance to settle. And generally these will be like 1,000-barrel tanks. Our tanks outside are 400 barrels. They're using 1,000-barrel tanks with just, depending on that cross-sectional area, and lots of time for the oil and water to segregate. Then they take the oil off the top, water comes off the bottom, back through our grasshopper again. And it's also got the variable weir to adjust the height in here. So this is and Oxy's reason is for energy conservation, instead of using that heat to separate and get good oil. So it works great when the weather's warm. If the weather gets real cold, what's going to happen?
Not gonna separate out.
Not going to separate. And what they actually have to do sometimes is tie in their a hot oiler, which is just a truck with a big heating unit on it. Back it up there and tie it into the line and circulate it until they get good oil going again. They said they don't have to do it often, but it happens. So you look for these on that Oxy trip. These were also used early days of the oil field before treaters became very common. I've only been at it 48 years. I don't ever remember using a gun barrel. So I thought they were out of style. And we went out there, and there they were. Okay, questions on that? Let's go over and look at some dump valves and pressure regulators. These are the same valves we saw outside, pressure regulators. The pressure regulator is set by screwing this in and out. Somebody's messed with this and made it hard to do.
Duct tape it.
Huh?
Duct tape it maybe.
Oh. They work on the same principle as this little small regulator does. When I screw down, I'm tightening down on that spring. And as you push down on the spring, if I've got a diaphragm with the gas pressure acting on the bottom, is it going to be harder or easier to open? As I approach, keep screwing it down, screwing it down, screwing it down, I almost make this a solid steel bar, don't I? And so it's much harder for this regulator to push open. It would take more pressure. And so as I screw it down, I increase the back pressure on my vessel. As I unscrew it, come back off of it, there's a spring in here, just like this, that opens up. And now, this spring is more relaxed, and as I put pressure on my diaphragm, it'll open easier, so I'll have less back pressure applied to my vessel. And so these pressure regulators have a pressure gauge on them, and we adjust here until we have that pressure where we want it. And then we stop. And this has the seats, the diaphragms that move up and down to act on this pilot. This pilot is sensing the pressure downstream and allows pressure to flow to the diaphragm based on where we've set this spring. So the diaphragm and the spring work together or against each other, depending on how you want to look at it, to open and close and regulate and hold that gas pressure constant. There's a piece of tubing missing right here. This is the valve that we saw on which vessel?
Separators and free water knockout.
Yeah, free
Yeah, the free water knockout had one of these on the water dump, and the vertical separator had it on the fluid dump going to the free water knockout. And all it is this handle moving a valve off and on seat inside that valve body. Where did we see this valve? Yeah, it's a heater treater. It's got a pretty heavy weight on it. This is actually harder to lift than the ones out there were. And this is the same principle. Here's our equalizing line. This is just a filter to blow down liquids on that might get in the gas. And then hold that pressure on here so that the only thing that makes this move is that hydrostatic column of water, like we saw in the oil dumps and the water dumps. Okay, these are turbine meters. Remember we talked about turbine meters out there? And if you look in the flow path going through there, hello, can you see that blades in there? Maybe it looks like looking in a jet engine. So as the flow goes through there, it turns those impellers. Each one of those turns represents so much volume. And then this meter records that volume and we read in cubic feet of gas, direct reading. We can also take those counts off electrically or electronically and do it from a central point. A lot of our oil field automation uses pressure transducers like this one that send a signal back to a point, either in changing pressure, changing rates, and they'll send a signal back that's 4 to 20 milliamps. So why do we choose a range from 4 to 20? Why not go 0 to 20?
Gotta have some power to start, right?
Yeah, these have got to be powered up. So if it was powered up and I read 0, what would I assume if this was a flow meter?
Nothing?
No flow.
Zero.
Okay. What if it's not powered up? If it's a power failure?
Zero flow.
It's 0, but it's just really power failure. And so by doing the 4 to 20 milliamps,
You know when it's failed and.
you know when it's failed on power or when you're actually getting a good signal for whatever it is you're trying to get that flow back to. And there's, instrumentation, electronics engineers that'll be following that. Turbine meter works very similar to this one. You can see inside that senior fitting. And you can see, if you look at it now, you can see all the way down to the pipe. And then if we close the slide, yeah. Now you can see, whoops, when you look in there, now that slide's closed. We got all the pressure trapped in the pipeline down below it. So that means we can use this and crank our plate up. Y'all see that over there? That slide is what I moved with this. And then you can open it. It's open full up, and then when we crank this one, we need the other pieces to really show this well. You see those wheels moving on the side? Those are the gears that move that plate up and down. It's got little cogs on it too, where those catch and move the plate in and out of the stream. That's how that works. Okay, questions on any of this stuff? There is a centrifugal pump in this room. And do y'all see it anywhere? Where? Okay, that's the centrifugal pump. They're easy to tell. Schematically, you always draw them where the suction comes in the eye of the impeller. So the suction comes in here. This has got like blades on it. As those blades turn, they increase the velocity of the fluid out to the side where it's discharged. So this is the discharge piping. Big suction, smaller diameter discharge. And centrifugal pumps are generally driven by electric motor. Don't have to be. This is close coupled. The ones we saw out there had a pump setting kind of as a separate unit and a motor as a separate unit. This is all one integral unit. And so as that speed increases or the type of impeller that we use changes, we can get more pressure out of here. And we'll study this later where we look at pump curves for different centrifugal pumps and determine the head that's put out. And everything's measured in feet of head of water instead of pressure. And then rate. We find a curve that just fits our application. That's the size that we would order for this. Where else have you studied about centrifugal pumps? How about an artificial lift? Huh?
ESP.
Yeah, an ESP, electric submersible pump, is a centrifugal pump. And let's look right over here. This is a small section of an ESP pump. And so as this rotor turns, the motor section would sit here, and as this motor turns, it turns these impellers. And the individual impellers look like this. The fluid is directed to the middle, and it throws it out to the edge. It has a diffuser in it that as that fluid gets thrown out to the edge, it directs it back to the middle of the next one to increase it. So as we stack these stages up in here, we go from lower pressure to higher pressure to higher pressure to higher pressure, depending on the number of stages we put in the pump. And that's how the electric submersible works, or ESP. When we go to Oxy and a lot of other places, you'll see these on the ground being used, but they turn them like this. Now they lay them out horizontally. They bring the fluid in one end, discharge it out the other end. And so that horizontal pump can be used for water flood applications where you're needing to pump a lot of water at higher pressure. And you can use it's a modified submersible electric pump just laying on site. They call it an H pump. Tricky name, huh, for horizontal? But you hear them talk about their H pumps. And that's all that is a series of multiple stages linked together. And the more stages you have, the higher pressure you can get. Questions? Okay, let's go take one quick look at the wellhead model over there. So this is cutaway, takes it all the way from the bottom of the production string all the way up to a sucker rod pump, rods to the top of the well. And remember, down at the bottom of the hole, we made a conscientious effort to separate the gas from the oil. We don't want the gas going through our bottom hole pump, right? Reduces efficiency, creates mechanical problems for us. So we try to get all the gas flowing up this annulus between the tubing and the production casing. And we want our liquids just inside the tubing so that we can pump them with our sucker rod string. So we did all that work at the bottom of the hole to get it up to the top. It continues all the way through the tubing with the liquid, all the way to the annulus with the gas. Here's our casing head holding our surface pressure. And then we come to the tubing head. And at the tubing head, all that gas you worked so hard to remove at the bottom of the hole, you recombine it. Because now our liquids are trapped inside the tubing. And look at this stuffing box. Remember how big the stuffing box was on the wellhead out there? My hand would just about cover all of it. And this is at least twice that much. And it's got this many more packing rings in it to hold the pressure. This is a 2000 PSI rated wellhead. These are like used on the unconventional wells where you got a lot of gas coming. They'll also have a back pressure regulator on some of them. Depends on company policy whether they want to even regulate more gas here. But essentially we're taking the liquids out down to the flow line and then recombining this gas that we separated down hole right here to go in that common line to the batteries. Cool? Now, on high pressure wellheads, all these parts you see here are either slips or tubing hangers for high pressure wellheads. Lot huskier, beefier. Here's one of the chokes. So remember we looked at the choke bodies out there on the wellhead. We also saw a choke in the line heater. Flow comes in this way, and then we adjust the opening here. And what we're adjusting is this point going down into a seat, a tapered seat in there. So as we screw it down, we get more and more resistance to flow because we're making the opening smaller. As we open the choke, we're pulling this tapered body up out of that seat that's in down there to get more flow through it. So this is what the choke is doing while we're moving it. It's designed to just 2 bolts hold it on so that we can change it easily. Chokes are some of the worst things in the world to get cut out, either with sand in the production stream or just a high velocity gas flow stream. Some of the harder seats are made out of ceramic or a high strength metal to keep them from eroding so fast. So that's part of your, first part of your production system, almost first part of the facility coming in on high pressure gas is that choke. And a lot of difference between the wellhead this goes on and the pumping unit wellhead, right? We got to get some more models of the high pressure stuff cut away. Okay, questions on anything? I made up my time. Okay, honestly, has this been any help at all?